How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at Bohr Model and energies of principal energy levels. So our objectives will be to apply the Rydberg Formula and the Bohr Model of the atom to quantitatively determine the energy of various principal energy level transitions. So long story short, what is the energy change when we go from like energy level 3 down to energy level 2? And also describe the important features of the Bohr atom. So let's get going. Let's start with the continuous spectrum. So as most common sources of light produce many different wavelengths of light. For example, sunlight is producing this continuous spectrum. It's producing all the wavelengths of light. Incandescent bulbs, the old school ones with the filament that gets really hot and emits light, they're also producing many different wavelengths of light. These blend into each other to create a continuous spectrum. So all that means is there's no blank spots in what wavelengths are produced. So it looks like a rainbow. You've seen this in rainbows. It's splitting up the wavelengths of light and you can see it's continuous. There's no blank spots. It's filled in. This is in contrast to line spectrum. So when different gases are placed in low pressure tubes with high voltages applied, they emit different colored lights. For example, here's two different gases in a gas tube. And they've been excited with voltages, and you can see they're giving off a particular color. And when you look at what wavelengths of light are being produced, you only see bright lines at specific wavelengths. So this is what those two tubes produce. You're not going to see a continuous spectrum. You're going to see bright spots, bright lines being produced. So we call them line spectrum. So let's take a look at hydrogen's line spectrum and the Rydberg equation. So in 1885, a Swiss school teacher, Johann Balmer, observed that the wavelengths emitted by hydrogen fit a simple equation. And this is that simple equation. 1 over the wavelength has to equal RH, which is a Rydberg constant, times 1 over n1 squared, where n1 is just some positive integer, some whole number, minus 1 over n2 squared, where n2 is the larger positive integer. So no explanation as to why it follows this pattern, just establish that they do indeed follow this pattern. It would take decades to figure out why, right? But I won't keep you in suspense. I'm not going to make you wait decades. N's represent the energy levels that the electrons move between when emitting or absorbing light. So there, cat's out of the bag. So an example math problem that you need to be able to do with this equation would look like this. What is the wavelength of light associated with the transition from the third energy level to the second in an atom of hydrogen? So again, we have this equation. This time it's asking for wavelength. So all right, well, let me rearrange to get wavelength. Wavelength is going to equal 1 divided by that whole other side, RH times 1 over n1 squared minus 1 over n2 squared. So now I can just plug and chug. I got 1 divided by that constant, which is 1 point, I'm just going to say 1, 0, to keep 3 sig figs, times 10 to the 7 meters to the minus 1, then times by 1 over the, where is it? 3 and 2. So 2 squared minus 1 over 3 squared. And when I plug and chug that, I end up with 6.56 times 10 to the minus 7 meters. If you got a negative sign, you can't have a negative wavelength. All that means is that you kind of switched the order of these guys. So if you got a negative, you just ignore it. The wavelength has to be positive. You can't have a negative distance, all right? All right, so Bohr's model of the atom. He was like, how do we explain distinct energy levels or energies being emitted? How is this possible? What's going on here? Bohr's like, all right, well, I got an idea. If the electrons follow an orbit around a nucleus like planets around the sun, kind of looks like this. That would start to explain it. And he proposed 3 postulates. 1, only orbits of certain radii with certain definite energies are permitted for electrons in an atom. So it has to be in these particular orbits. An electron in an orbit has a specific energy and does not radiate or lose any energy. So that electron going around in that first energy level right now, not giving off any energy, not absorbing any energy. It just has a certain amount of energy and it's doing its thing. Third postulate, energy is only emitted or absorbed by an electron as it changes from one energy state to another. It's emitted or absorbed as a photon, and we have the energy equals that h nu, the Planck's constant times the frequency. So here's a little demonstration. Boom. Photon of light comes in, interacts with the electron, photon of light gets absorbed, and that electron gets kicked up to a higher energy level, right? So energy states of the hydrogen atom. Bohr's like, all right, well, let me look at classical equations for motion, because those exist already, and interacting charges, and those exist already, and see if I can describe these orbits' energies. And he's ended up with this equation, right? E equals this negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n, again, is an integer representing the quantum number. So the first orbit would be the closest one to the nucleus, right? And all energies are negative. So all these like orbits have a negative energy. And the lower the energy, or the more negative it is, the more stable the atom is. So if I'm an electron, and I'm in that first energy level, I'm in the ground state. I'm in the lowest possible energy state. As n increases, energy becomes less negative and therefore less stable. So as n approaches infinity, the energy associated with that approaches zero, and that's the highest energy state possible. So if instead this electron, instead of being on that first energy level, was, let's say the third, it would be in the excited state because it could be at a lower energy. All right, so now we got some more math, everybody's favorite, right? So we know that a change in energy has to be the energy at the final state minus the energy at the initial state, right? That's just the change in. We also know that it's going to be equal to this kind of setup because we know that from what we previously stated, the energy is equal to this constant times 1 over the n. So the change in the two can be represented by this. We also know that energy is equal to h nu and also hc over lambda. So watch this, a little algebra, little algebra. Well, if I know, energy equals hc over lambda, let me plug it in to right there. And then I have hc over lambda equals this other nonsense, but let me get lambda by itself. So I divide each side by hc, and hey, wouldn't you know it? This looks familiar. 1 over the wavelength equals, these are all constants, some constant times 1 over n f squared. Hey, I know this equation. It's the Rydberg equation. That constant, those three constants together, is our h. It's showing the same relationship as the Rydberg equation. So what we're able to deduce from this is that each bright line represents its transition between energy levels. So if I started at energy level 3 and I dropped down to 2, the energy associated with that transition is giving me this red wavelength of light. And if I look from 4 to 2, is giving me this teal wavelength of light. If I'm going, 6 down to 2, because I skipped 5 over there, that is 5. 5 down to 2 is this one, and then 6 down to 2 gives me the violet wavelength. So these bright lines are being emitted when the energies from the electrons are being emitted when they fall down an energy level. So limitations of the Bohr model. Turns out the Bohr didn't have it all right. So the math works out nicely for hydrogen, but this equation fails to describe any other nuclei and their orbital energies and their spectra. So it's great for hydrogen, doesn't work for anything else. And the reason for this is, turns out hydrogen is the simplest system we can look at. It's one proton and one electron. We don't have multiple electrons, so they, aren't interacting with each other. Electrons don't act like planets when they're orbiting the sun either, turns out. And also electrons have wave properties to them, so they definitely don't look like planets, revolving around the sun. But it's still useful, and it introduced two concepts that are part of our current understanding and current model of the atom. First one being electrons exist in discrete energy levels described by quantum numbers, which we'll get into, and the energy is involved in moving electrons from one level to another. So summarize. Can you apply the Rydberg formula in the Bohr model of the atom to quantitatively determine the energy of various principal energy level transitions? I hope so. Can you describe the important features of the Bohr atom, the ones that have still stuck around? I hope so. All right, okay, bye.